All right, we're going to round out our discussion of the various convergence tests by talking about alternating series in 9.6. And this is one of my favorite sections in probably everything that we teach at COS, because I think that there's some really truly amazing facts that we talk about here, and we're probably not going to be able to dig in too deeply, unfortunately, but this kind of stuff I think is just fascinating. But anyway, let's get into it. So first of all, an alternating series is a series of one of these forms where we're assuming that the AKs are positive. So, every other term is going to be negative. So maybe the first term is negative, and then the first, third, fifth, seventh terms are negative. Or maybe it's the even terms that are negative. But anyway, these are alternating series. And so these are the topic of discussion in this section. When you're dealing with an alternating series, one of the ways that you can deal with it is to take the absolute value of the terms, of the series, and then see if the absolute values converge. Okay. So if the absolute value of the series converges, then the original series without the absolute values is said to converge absolutely. Or another way we say that is we say it's absolutely convergent, right? So a series is an absolutely convergent series if its absolute value, if the series of absolute values converges, right? And it's called absolutely divergent, or it's said to diverge absolutely if the series of absolute values diverges. So let's practice. Let's determine whether these two series converge absolutely. So the first one is actually, it's not an alternating series according to the definition that we wrote down a second ago, because the sign isn't alternating on every other term. It's actually 1 minus 1/2 minus 1 over 2 squared, and then plus 1 over 2 cubed, plus 1 over 2 to the fourth. So it's not quite alternating on every other term, but but we can still apply the previous fact, right? The previous theorem. So to see if this series converges absolutely, right? We're supposed to see if this thing converges absolutely. So to determine if this thing converges absolutely, we can just look at the absolute values, right? So if I call this thing, maybe we can call this thing the sum from k equals 1 to infinity of u sub k, or whatever, right? So if that's the case, then the sum from k equals 1 to infinity of absolute value of u sub k is going to be 1 plus 1/2 plus 1 over 2 squared plus 1 over 2 cubed, right? And so forth. And this is just the series of 1 over k, not k squared, sorry, 1 over, what would it be? 2 to the k. Other way around, right? 2 to the k. And I suppose we're starting at 0, actually, right? Yeah, then we get 2 to the 0 is 1. 2 to the first is 2. 2 squared, 2 cubed. Okay, so this is 1 over 2 to the k. Note that this thing is convergent. This is a geometric series, right? So we can say the sum from k equals 0 to infinity of 1 over 2 to the k equals this thing, which is geometric with common ratio r equals 1/2, and that's less than 1. Therefore, the sum, and I started it up at 1 here. I guess I should have started at 0. Okay, but anyway, the sum from k equals 0 to infinity of absolute value of uk converges, and thus the sum from k equals 0 to infinity of uk without the absolute values converges absolutely. Okay. So yeah, the series converges absolutely. Okay, let's look at another one. Okay, so let's do 1 minus 1/2 plus 1/3. This one is alternating, right? It alternates. Plus 1/5 minus and so forth. Okay, so anyway, if I again call this thing sum from, this time I'm going to start at 1 for sure. From k equals 1 to infinity of uk, then the sum from k equals 1 to infinity of absolute value of uk would be 1 plus 1/2 plus 1/3 plus 1/4 and so forth, right? And that's just the sum from k equals 1 to infinity of 1 over k, right? So that's just 1 over k. So this thing we know to be divergent, right? Because sum from k equals 1 to infinity of 1 over k is a p-series with p equals 1, which is, greater than or equal to 1. So the sum from k equals 1 to infinity of the absolute value diverges, and therefore the sum from k equals 1 to infinity of uk without the absolute values diverges absolutely. Okay, so that's how absolute convergence and divergence works. Now, importantly, well, actually, we're going to see this here in a second, but importantly, if a series converges absolutely, then it converges. But if a series diverges absolutely, it may or may not diverge. It could still converge, potentially, right? So when we say that it diverges absolutely, we're not saying, oh, it's set in stone, right? It's never going to converge. No, that's not what we're saying. When we say it diverges absolutely, we mean that the absolute value, the series of absolute values, diverges. And that's where the word absolute comes from. But the original series itself, this series up here, the alternating series, it could potentially still converge. We don't know. We'd have to do a little bit more work. So let's talk about that. Let's talk about how you would figure that out. Okay, so if a series converges absolutely, then it converges. If a series diverges absolutely, then it may or may not converge, right? So that's theorem 9.6.4. And we could almost skip this example. It's kind of silly, but it says, example 2 says, show that the following series converge. The first one is this series that we just looked at, right? Well, what we showed in example 1 is that it converges absolutely. And since it converges absolutely, by theorem 9.6.4, it must converge, right? So yeah, so this thing converges, right? It converges absolutely, therefore it converges. For this one, on the other hand, we'd have to do a little bit of work. So let's work on this one. Let's see if this thing converges. Okay, to determine whether or not it converges, I'm gonna see if it converges absolutely, because, and this is a little tricky because you may not notice this right away, but notice that for some values of k, cosine k is going to be positive, and for other values of k, cosine k is going to be negative, right? So let's take a look at that one. It's kind of an interesting case. So example 2. Part A. Well, part A was just this same series. Yes, 1 minus 1/2 minus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th minus 1 over 2 to the 5th minus etc. converges. Because it converges absolutely. Okay, but what about this guy? What about this second series? The sum from k equals 1 to infinity of cosine k over k squared. Okay, now this is not very nice, right? If it was cosine pi k or cosine k pi over 2 or something like that, it might be a little bit nicer to work with. But just cosine k, it's like you're thinking cosine of 1, cosine of 2, cosine 3, radians, right? It's always in radians unless otherwise specified. So cosine of 1 radian, cosine 2 radians, none of those values are going to be very nice to compute, right? Fortunately, we don't have to really worry about that, because if you take a look at the absolute value of this thing, absolute value of cosine k over k squared, well, what do we know about this? We know that cosine always lives between -1 and +1, right? So this has to be true for any value of k. And so that means that the absolute value of cosine k has to be less than 1, right? These two things mean the same. They mean the same thing. Okay, well, so if that's true, then the absolute value of cosine k over k squared is always going to be, well, and I should really be careful here. It's really less than or equal to, right? But anyway, absolute value of cosine k over k squared is less than or equal to 1 over k squared. And, you know, you could still keep it in absolute values, but you don't really need to, because 1 is a positive number, okay? So taking absolute value of 1 is not going to change anything. And k squared is always a positive number, because first of all, k is positive, but second of all, even if it were negative, when you square it, you'd get a positive answer. So this is just 1 over k squared. Okay, so you may or may not have enough practice at this point to kind of see where I'm going with this, but what I'm going to do is I'm going to use a direct comparison, right? I'm going to say, well, I know that this thing converges, and it's the larger of the two series, right? This is the smaller of the two series. So if the larger one converges, then the smaller one converges by direct comparison, right? That's just a direct comparison test. So what have I shown, right? I've shown that the absolute value of this series converges, and therefore this series converges absolutely. And since it converges absolutely, it converges. Okay? So let's write that all out. Okay? So I can say, so the sum from k equals 1 to infinity of 1 over k squared converges. Right, it's a p series with p equal to 2, which is greater than or equal to 1. Or greater than, sorry, it needs to be strictly greater than 1. Right? Which reminds me, up here on example 1 part B, I really should have had this, right? I really should have said less than or equal to 1. That's the condition that causes it to fail. Anyway, I apologize for that. But yeah, so the p series here with p equal to 2, which is greater than 1, so this thing converges. But sum from k equals 1 to infinity of absolute value of cosine k over k squared is less than or equal to the sum from k equals 1 to infinity of 1 over k squared. So sum from k equals 1 to infinity of absolute value of cosine k over k squared converges by the comparison test. Okay? Thus, I'm going to try to squeeze this in here. Thus, the sum from k equals 1 to infinity of cosine k over k squared without the absolute values converges absolutely, and therefore sum from k equals 1 to infinity of cosine k over k squared converges. Whew. All right. So I managed to squeeze it in. But there you go. So there's the justification. This thing converges, and here's how we know, right? By a direct comparison. By a direct comparison, the absolute value converges, and therefore the original series converges. Okay. So that's all well and good, but what if you have a series that is absolutely divergent, right? It diverges absolutely, but how would we know whether or not the original series converges, right? So first of all, just terminology, right? A series that converges but diverges absolutely is said to converge conditionally. And I know that this is probably starting to get a little confusing, so let me rephrase that, right? If you have a series that converges, but the series of absolute values diverges, then we say that the original series converges conditionally. Okay? So when you're dealing with alternating series, or not necessarily even alternating series, if you're just dealing with series where some of the terms are positive and others are negative, right? You have two different kinds of convergence that you can talk about, right? So you have absolute convergence, which is when the series of absolute values converges. And then you have conditional convergence, which is where the series of absolute values diverges, but the original series itself converges, right? That's conditional convergence. Okay? And then, of course, you still have divergence altogether, where, the original series diverges. Okay? So now, how can we figure out if the original series converges? Like, if the series of absolute values diverges, how can we figure out if the original series converges or diverges? Well, there's a really easy test that we can apply, and it's called the alternating series test. So here's how the alternating series test works. Let's say that you have an alternating series that looks like this or looks like this, where the AKs are positive, right? These series are going to converge if the sequence of the AKs is eventually decreasing. Okay, it doesn't even have to be decreasing all the time, nor does it have to be strictly decreasing, but it does need to be eventually decreasing. Okay? So if the sequence of the absolute values, really, of this term is eventually decreasing, and if the limit of the AKs goes to 0, then these series converge. Okay? So let's take a look at some examples of that. So here's what I want to do for the next 4 examples. I want to, first of all, determine if the series converges absolutely. Okay, so we'll look at the absolute value of the thing and see if the absolute value of the series converges, and then if it does, we're done, right? If it doesn't converge absolutely, I want to see if it converges conditionally by applying the alternating series test, okay, that we just looked at on the previous page. So that's our task. We're going to determine if the series converges absolutely, and if not, determine if it converges conditionally. Okay, so let's take a look at some of these things. Okay, so let's look at the sum from k equals 1 to infinity of negative 1 to the k plus 1 times 1 over k. Now, actually, we already looked at this thing. It's just that we actually wrote out the terms. So this was example 1b, right? This was example 1b. This is just when k is 1, this is a positive, and we get 1. When k is 2, we get negative 1/2. When k is 3, we get positive 1/3, and so forth. Right? So we've already looked at this series. And we know that this is not absolutely convergent, okay? Because we already looked at that. We already did that in, for example, 1b, right? Because if you take the absolute value here, you're just going to get 1 over k, right? So maybe I'll write it again. So note, sum from k equals 1 to infinity of absolute value of negative 1 to the k plus 1 times 1 over k equals the sum from k equals 1 to infinity of 1 over k, right? It just gets rid of the negative, that negative 1 to the k plus 1. And this thing, which diverges, right? This is divergent, right? And I know that it diverges because it's a p series with p equals 1, which is less than or equal to 1. Okay? So this series is not absolutely convergent, but maybe it's conditionally convergent, right? Right, so is not absolutely convergent. However, let's apply the alternating series test. So for the alternating series test, we're going to check two things. We're going to check to make sure that the a sub k's are eventually decreasing. That's what you get when you ignore the alternating part. Okay, so we're going to check that that's eventually decreasing, and we're going to check that the limit as k goes to infinity of that portion of the sum goes to 0. Okay, so let's check the first condition, right? So note that, and maybe I'll label it. I'll say, so we're going to apply the alternating series test. Okay, so for the alternating series test, now condition 1. Note that 1 over k is decreasing. That's a really simple thing. There's nothing to show there, right? It's like it's obvious. As k gets larger, the fraction gets smaller. So this is decreasing. So that condition holds. And the second condition is that you have to look at the limit as k approaches positive infinity of 1 over k. And as k gets really large, this fraction is going to get really small. So this goes to 0, right? So that condition also holds. So by the alternating series test, the sum from k equals 1 to infinity of negative 1 to the k plus 1 times 1 over k converges. Okay, so what do we have? We have a series that's not absolutely convergent, but that is convergent nevertheless. And so we call this thing conditionally convergent, right? So we say, therefore, the sum from k equals 1 to infinity of negative 1 to the k plus 1 times 1 over k is conditionally convergent. Okay, so now here's one of the crazy things about series that are conditionally convergent like this one, right? So this is the harmonic series. We actually proved by looking at the sequence of partial sums like a few sections ago, we proved that this thing diverges. But here's the crazy thing about conditionally convergent series like this alternating one. You can rearrange the terms of the series so that it adds up to be any real number you like. Okay, so if you lay out the terms the way that they are here in order, then this actually adds up to be the natural log of 2, which is kind of a crazy fact in and of itself. right? But if you rearrange the terms and add them up in a different order, you get a different answer, which is just kind of crazy, right? It's just kind of crazy. It's one of those things. It's like you assume that addition is commutative, and it is if you have a finite number of terms, or if you have an infinite number of terms and the series is absolutely convergent. But if you've got an infinite number of terms and the terms are conditionally convergent, then you can add those things up in any order to get any answer you want. So it's just kind of a crazy thing. I just think that's like an absolutely fascinating thing. I can't prove it. I mean, I could prove it if I sat here and worked at it for a long time, but you don't want to see me suffer like that. But it's fascinating, and it's something that you would learn in a real analysis course. So anyway, I just think that's really cool. Moving on, let's do another one. So let's do sum from k equals 1 to infinity of -1 to the k plus 1 times k plus 3 over k times k plus 1. Okay, so same goal as before. We want to see if this thing is absolutely convergent, and if it's not, then we're going to see if it's conditionally convergent. Okay? So, if we look at the absolute value here, then we just get the sum from k equals 1 to infinity of k plus 3 over k times k plus 1. And the question is, does that thing converge? So let's apply a test to see. I mean, my feeling on the matter is that this looks like k. Okay, so if I just look at kind of the big picture, it's like a k over a k squared type of a situation. That would be the same thing as like a 1 over k type of situation. And I know that 1 over k diverges. It's the harmonic series. So my suspicion is that this thing diverges. So I'm going to compare this to a series that I know diverges. And I think what I'm going to do is use the limit comparison test, right? So I did a direct comparison test when we were looking at the cosine, right? We did a direct comparison here to show that that thing converges. I think I'm going to use a limit comparison here. My other options are I could use the ratio test or the root test, but I don't think if I take the kth root, I don't think that's going to end up very nice. If I take if I do k plus 1, if I do a sub k plus 1 divided by a sub k, I don't think that's going to end up nice either. So ratio test, root test, I don't think they're going to be very nice. But I can do a limit comparison test. And what I'm going to compare this to with my limit comparison test is 1 over k. And remember, the way the limit comparison test works is you take the limit as k goes to infinity of this thing over whatever it is you're comparing it to. And if you get if your limit is bigger than 0, but if your limit's a finite value bigger than 0, then the series either both converge or both diverge. And since I know that 1 over k diverges, if I do that limit comparison and I get a finite value that's more than 0, then I can safely say that this thing also diverges by the limit comparison test. So let's do that. So I'm going to take limit as k goes to infinity of k plus 3 over k times k plus 1 all over 1 over k. When I flip and multiply, this k will cancel that k. So this is really limit as k approaches infinity of k plus 3 over k plus 1. Well, and that's easy to do, right? This is just a polynomial divided by a polynomial, so the limit is the ratio of the leading coefficients, 1 over 1, which is 1. So 1 is bigger than 0, but it's also a finite value, and therefore this series does whatever this series does. This series diverges, therefore this series diverges. Okay, so I can say by the limit comparison test, since 1 over k diverges, k plus 3 over k times k plus 1 also diverges. Okay. Well, all right. So that just means we have more work to do because this was not our original series, right? This was our original series. It was alternating. So now we have to apply the alternating series test. We know that this thing does not converge absolutely, but it could converge conditionally. And so to see if it converges conditionally, we need to apply the alternating series test. I almost feel like the alternating series test should be renamed. I think it should be called the Conditionally Convergent test, right? Because it's something you would do after you've already determined that something is not absolutely convergent, but maybe it's conditionally convergent, right? But anyway, so let's take a look at the alternating series test. Again, there are two conditions we have to check here. The first thing is that we need these terms to be eventually decreasing. Okay? There are a few different ways that you could establish that. One way that you could establish that this is decreasing, I mean, first of all, I suspect that it is, right? Because the degree of the numerator is less than the degree of the denominator, so the denominator should grow faster than the numerator. So there might be a couple terms right at the beginning where, where this thing increases, but eventually it's going to start to decrease, and it's going to start to decrease, and it's going to continue to decrease because the denominator is just going to grow faster than the numerator. But to show that, right, to show that mathematically, there are a couple things you could do. One thing you could do would be to look at a difference of consecutive terms. Right, so we talked about this earlier on in the chapter, like 9.1 or 9.2, something like that. So we could look at the difference of consecutive terms, or we could look at the ratio of consecutive terms, or we could look at the limit limit as k goes to infinity, which actually we're going to do for condition 2 anyway. So let's look at the ratio. Let's look at a ratio of consecutive terms. Yeah, because I'll get a k plus 1 there that I can cancel with that one. I don't know. I think it'll work out. Maybe, maybe not. So I'm going to say a sub k plus 1 divided by a sub k equals k plus 4 over k plus 1 times k plus 2 times k plus 1 over k plus 3. Well, maybe this is not as nice as I was thinking. We do get some cancellation. Not a ton, though. In a way, this is even worse than worse than what we had before. So what do we get? We get k squared plus 4k over k squared plus 5k plus 6. Goodness gracious. Well, yes. All right. So now I can see pretty clearly, though, right? the denominator here is always going to be bigger than the numerator, isn't it? Because 5k is bigger than 4k, and 5k plus 6 is even bigger than 5k. So 5k plus 6 is always bigger than 4k if k is a positive integer. So if the denominator is always bigger than the numerator, then this fraction is always less than 1. Okay? So this is less than 1 for all k. All right? So since the ratio of consecutive terms is less than 1, that means a sub k plus 1 is smaller than a sub k. Right? So the a sub k's are decreasing. So therefore, ak is decreasing. Okay, so that first condition holds. We've shown that the ak's decrease. The second condition is we need to look at the limit as k goes to positive infinity of k plus 3 over k times k plus 1. And we need to make sure that this thing goes to 0. It does, right? I mean, this is limit as k goes to positive infinity of k plus 3 over k squared plus k. And because the degree, these are both polynomials, the degree of the denominator is greater than the degree of the numerator, and so this is going to go to 0 for sure, right? Okay, so both of the conditions in the alternating series test check out, and therefore the series converges. Now I've run out of space. Maybe let's write it here. So we'll say so the sum of negative 1 to the k plus 1 times k plus 3 over k times k plus 1 converges, but not absolutely. Therefore, it converges conditionally. All right. So two conditionally convergent series. Now I'm not sure. So the first one we looked at, I know that that converges to ln of 2 if you add the numbers up in this order. If you add them up in a different order, it converges to something else, which is weird, right? But this one I have no idea. I have no idea what it converges to. It doesn't matter. We weren't asked to find the sum, right? Okay, let's look at another one. We weren't asked to find the sum. We were just asked if it converges. And it does. It converges conditionally. Okay, let's look at this one. We've got sum from k equals 1 to infinity of negative 1 to the k times 2 to the k over k factorial. Okay, so first of all, I'm going to determine if this thing converges absolutely. So I'm going to take the absolute value. Okay, and now this thing, to see if this thing converges, I see a factorial, and that just automatically in my mind means ratio test. You want to do the ratio test for sure. So so let's do it. So for ratio test, we look at the limit as k goes to infinity of a sub k plus 1 divided by a sub k, right? So that's the limit as k goes to infinity of 2 to the k plus 1 divided by k plus 1 factorial times k factorial over 2 to the k. And that's 2 times 2 to the k over k plus 1 times k factorial. I love this. sorry, 2 to the k. These things are the best, right? 2 to the k. Those cancel. Those cancel. We get limit as k approaches positive infinity of 2 over k plus 1. As k gets large, this fraction is going to get small, so this goes to 0, which is less than 1, right? Remember, the ratio test is inconclusive if the limit you get equals 1. But if the limit you get is less than 1, then you can say that the series converges. If the limit that you get is greater than 1, then you say the series diverges. If it equals 1, inconclusive. But in this case, it's equal to 0, which is less than 1. So, by the ratio test, the series, I'll write it here. The series k equals 1 to infinity of 2 to the k over k factorial converges. Oh, that's nice, because our work is done then. Because if the absolute value converges, then the original series converges, right? So we can say, thus, the sum from k equals 1 to infinity of negative 1 to the k times 2 to the k over k factorial converges absolutely. And hence converges, right? Okay, but it converges absolutely. So we don't need to check if it converges conditionally, because it doesn't, right? It converges absolutely. So we're done. We're done there. Okay, one more example. Let's do sum from k equals 1 to infinity of negative 1 to the k times 2k minus 1 factorial over 3 to the k. Okay, so I'm going to skip the step where I take the absolute value, because I think you see what happens is that this thing just goes away. And I'm going to focus on this guy, the 2k minus 1 factorial over 3 to the k. And I think I'm going to apply the ratio test there. Because it's got a factorial in it, right? So I'm going to have 2 times k plus 1 minus 1 factorial over 3 to the k plus 1 times 3 to the k over 2k minus 1 factorial. So let's think this through. This is going to be 2k plus 2 minus 1. So that's going to be 2k plus 1. 2k plus 1. But I want to cancel it with a 2k minus 1. So I think I'm going to call this 2k plus 1 times 2k times 2k minus 1 factorial. And then it'll cancel with that one down there. This thing I'll call 3 times 3 to the k. And then the 3k's will cancel. Cool. Right, this guy, by the way, if you need some extra guidance, right, it's this thing, factorial, which is really just 2k plus 1 factorial. So I'm going to write it like this. (2k plus 1 times 2k times 2k minus 1 factorial. This is just 3 times 3 to the k. And beautiful, 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 beautiful. Okay. We get well, I'm going to distribute the 2k, I suppose. So we get 4k squared plus 2k over 3. Limit as k goes to infinity. Well, limit as k goes to infinity of that thing is just going to be positive infinity, which is definitely greater than 1, right? So by the ratio test, the series from k equals 1 to infinity of 2k minus 1 factorial over 3 to the k diverges. Okay, so since the series of absolute values diverges, we need to apply the alternating series test to see if the alternating series converges or diverges. And once again, I'm running out of space, but I'm gonna use the same trick that I did last time to give myself some more surface to write on. Okay, so I need to apply the alternating series test. Alternating series test. There are two conditions to check. First of all, we need to make sure that these terms are eventually decreasing. And I don't think they are. I think that that's the problem, right? I think that's why the thing diverges to begin with, because check it out. 3 to the k, let's imagine that k is a really big number, like 1,000. Then 3 to the 1,000 is just going to be 3 times 3 times 3 times 3, 1,000 times. That's big, but it's not as big as this, right? If k is 1,000, 2 times k minus 1 would be 2,000 minus 1, so 1,999. 1,999 factorial is going to be 1,999 times 1,998 times 1,997 and so forth, all the way down to 1. So here you're just going to have 3 times 3 times 3. Here you're going to have 1,000 and something times 1,000 and something times 1,000 and something. So this is going to be much bigger than that, right? And the bigger k gets, the larger the discrepancy. So I think this is actually an increasing thing. Probably the best way to show that it's increasing would be to look at a ratio of consecutive terms, because you've got that factorial in it, right? So let's do that, right? In fact, we've kind of done it already. I'm going to say ak plus 1 over ak equals 2 times k plus 1 minus 1 factorial over 3 to the k plus 1 times 3 to the k over 2k minus 1 factorial. The difference between this and what we did before is that we're not taking the limit as k goes to infinity. Right? We're not going to be taking the limit, but anyway, all the same cancellations would take place. So I'm going to skip this middle step and just cut to the chase and say, well, this is 4k squared plus 2k over 3. If k is 1, then this is 6 over 3, which is 2. If k is 3, then it's even bigger, right? As k increases, this thing increases, because you don't even have any k's in the denominator. So this is going to increase. So when k is 1, this is already 2, which is bigger than 1. And then as k gets larger, it's going to get even bigger than that. So we can safely say this thing is bigger than 1. So since the ratio of consecutive terms is bigger than 1, that means a sub k plus 1 has to be bigger than a sub k. Right? So the ak's are increasing. Okay, so I'm not even going to check condition 2 because condition 1 fails, right? So since condition 1 of the alternating series test fails, the series from k equals 1 to infinity of negative 1 to the k times 2k minus 1 factorial over 3 to the k diverges. It doesn't just diverge absolutely, it diverges period, right? So this thing is we could maybe call it like a completely divergent series, right? Or we can maybe call it conditionally divergent, I guess. But no, it's just completely divergent. The absolute value doesn't converge, but neither does the alternating version, right? So it's completely divergent. So there you go, right? So we've seen, so we saw two examples of series that were conditionally convergent, okay, parts A and B. We saw one example of a series that was absolutely convergent, that was part C. And then we saw one example of a series that's divergent, and that was part D. Okay, so hopefully that gives you a good feeling for how to go about these kinds of problems. I'm going to point out the following fact, though, and this refers back to part D. Well, actually part C and D. Because here, we used the ratio test on the absolute value, and we saw that the absolute value was convergent, and therefore the alternating thing was convergent. Here we did the same thing. We used the ratio test on the absolute value, saw that it was divergent, so then we decided to try to use the alternating series test. But in using the alternating series test, we ended up doing the same kind of work that we had already done when we applied the ratio test to begin with. And sure enough, found out that even the alternating series was divergent. And so that turns out to be true in general. So it is in fact the case that if you apply the ratio test to the series of absolute values, and you find that the series of absolute values converges, then so does the original series, right? That's obvious because an absolutely convergent series is convergent. But here's what's new. If you find that the series of absolute values diverges, then so does the original series, and you don't even have to apply the alternating series test. Okay? So your book actually gives this its own name. It calls it the ratio test for alternating series, but it's nothing new. It's the same test as before. Okay? It's just that it's just that with the ratio test, you don't even actually have to do the alternating series test. Once you've discovered that it converges, that the absolute value converges or diverges by the ratio test, then you know that the original series it does the same thing as the absolute value does. But that's only true when you're applying the ratio test. Actually, it's also true for the root test. I wrote this down. I was like, I think this is true for the root test too. But your book doesn't mention it. So I looked it up, and it is true. It's true for the root test as well. I'm not sure why the book doesn't mention... I'm not sure why the book mentions this for the ratio test, but not for the root test. But it's true for both of them. Anyway, so one last note. Okay. Actually, I'm going to pause this so that I can pull up the textbook. Okay, so this is on page 560 of your textbook. So it's at the end of section 9.6, and it's a summary of all of the convergence tests. So if your head is starting to swim a little bit because we've talked about so many different kinds of convergence tests, then this page is the page for you. I think this is a really great summary of all the convergence tests we've talked about. So first of all, you've got the divergence tests, right? So right off the bat, if the limit of the terms is not 0, then the series is going to diverge, right? If the limit is equal to 0, then the series could converge or could diverge. You just have more work to do. We talked about the integral test, the direct comparison test, the limit comparison test. So in this section, I gave you an example of each of those, okay, as kind of a review of those notions. The integral test, I didn't give an example of today, but we saw a few examples kind of at the beginning of the chapter. Okay, this is the one that says if the integral converges, then the series converges, and vice versa, right? Then you have the ratio and root tests. We saw a couple examples of the ratio test today. We didn't see any examples of the root test today, but you know, we've seen examples of it in the past. And then the new one was the alternating series test. Okay, and that's the one that we talked about today. And then they list, like I said, they list this ratio test for absolute convergence, where you're just doing the ratio test, but on the absolute values of the terms. It's the same test, right? It's the same test. It's just that if you apply the ratio test to the absolute values and you determine that the absolute values diverge, then the original series also diverges, right? So that's what's kind of new about this little piece. Basically, it means that if you conclude that the absolute value diverges by the ratio test, then you don't have to do the alternating series test to see if it's conditionally convergent, because it's not going to be. Anyway, so that's that. And technically, that's true for the root test as well. But anyway, that's that. And then this last column is really useful because they tell you when to try what thing. Like they're saying, you know, alternating series test. This only applies to alternating series. So don't do this on series that aren't alternating. Or the ratio test. Try this when the UK, you know, involves factorials or kth powers, right? Anyway, so I think this is a really good chart. Again, this is page 560 of your textbook. And that's all I'm going to say.